In this video, we'll be discussing a number of key reactions with alcohols and alkyl halides. So this is our first real encounter with reactions in this class, and we'll be focusing on one class of reactions in Chapter 5, and that is the reaction of an alcohol with a halo acid that generates the alkyl halide plus H2O. Now, this is not the only way to generate alkyl halides from alcohols. We can also take an alkyl halide and add the elemental X2 to generate the equivalent of Rx, and then an equivalent of HX off to the side. But the reaction we'll be focusing on in this chapter is going to be this top one here. So the reaction of an alcohol with an acid to produce the alkyl halide plus water. Now the reactivity of these this alcohol plus alkyl halide, there are trends for both the alcohols and the acids. So we see that for the acids, HF is going to be less reactive than HCl, which is going to be less reactive than HBr, which is going to be less reactive than HI. Our sweet spot for reactions is generally going to be this HCl and HBr addition to alcohols. In general, we see that HF is too non-reactive and we don't use it, and HI is too overreactive. In fact, it overreacts, and we often avoid that as well. So the sweet spot for this type of reactions is going to be HCl and HBr, and we'll see that this trends with acidity. So as the acidity of the mineral acid increases, the reactivity of the acid increases as well. Now for alcohols, we see that the trend is going to be that methyl reacts slower than primary, which reacts slower than secondary, which reacts slower than tertiary alcohols. And we'll examine the mechanisms for these reactions for all four of these types of alcohols. So this is for the the HX, and this is for the ROH. We'll examine the mechanisms for the methyl, primary, secondary, and tertiary alcohols later in this chapter. But for now, we just need to understand that methyl and primary are going to react slow, and secondary and tertiary are going to react much faster for this specific type of reaction using HX as a reactant to generate the alkyl halide. So let's look at an example of a reaction that we would see on paper, or one that we would do in the lab. So say we have this type of alcohol, so we have T-butanol, and we add HCl. And generally, this is done at room temperature. So this is a tertiary alcohol. So again, we see this is a tertiary alcohol. It's got 1, 2, 3 carbons attached to it. Tertiary alcohols in reaction with a mineral acid usually proceed at room temperature. And what that would do is we see a substitution of the OH with Cl, and we generate an equivalent of water. And this would be quite fast. Now, if we instead take a secondary alcohol, so let's instead examine cyclohexanol, and we add, say, HBr to it, this one would require a bit of heat, indicated by this delta symbol underneath the reaction arrow. We would indeed do the substitution reaction. We would substitute the OH for a Br and generate an equivalent of water. In this case, since we're adding heat, this would also occur fast. If we did it at room temperature, this would be slower. It would still proceed, but it would be a slower reaction. Now instead, if we take a primary alcohol, say this butanol, N-butanol, and we add HCl to the reaction, and we heat it because we already know it's going to go slow, we would do some amount of substitution to generate the alkyl chloride and then generate an equivalent of H2O, but this would be slow. So we see that the tertiary and the secondary alcohols are going to go very fast, and the primary, and if we did a methyl, in fact, would go so slow that we wouldn't even see this reaction. So this is a good way to substitute an OH for Cl. We see the substitution here. We substitute an OH for a Br. We see the substitution here. We substitute an OH for a Cl, and we see the substitution here. This is not the only way to change or exchange an OH for an alkyl halide, in this or do what we call the substitution reaction. So there are other ways to exchange an OH for an alkyl halide. So one of those ways, so we can exchange OH for Cl. One of those ways we can do that is the addition of what we call thionyl chloride, so SoCl2. So this is thionyl chloride. This is a powerful reagent. It's going to do a substitution reaction of OH with Cl. The mechanism for this is beyond the scope of this course, but a sample reaction would be ROH plus SoCl2 would result in RCl. So we've done the substitution. We've gone from ROH to RCl, and then that generates an equivalent of sulfur dioxide and an equivalent of HCl. So a sample reaction, say we have this benzyl alcohol, so we have this structure here, and we added thionyl chloride. We would substitute the OH for Cl, and we would generate again SO2 plus H2O. What we see is this does not result in inversion of stereochemistry, and we'll see that some of these reactions do. So if these are both up, this would not result in inversion of stereochemistry. The nice thing about thionyl chloride is it is also facile to do with primary and methyl alcohols. So while we saw that the previous method was slow with primary and methyl alcohols, this is just as easy with primary and methyl alcohols. So these would both go fairly well, even though this is a secondary and this is a a primary alcohol. They would both go easily. Another reaction we see is we can exchange OH for Br, and this is done by the addition of phosphorus tribromide. So the reaction scheme for this is we have 3 ROH plus PBr3 goes to, we generate 3 equivalents of the alkyl bromide, and we generate the phosphonate. Generally, we would just write 1 equivalent of the alcohol and generating 1 equivalent of the alkyl bromide, but understand that we do require 3 of each of these to make the reaction go forward. So an example reaction of this would be, say we have the methyl and an alcohol, and we add PBr3. I'll draw this below. We would end up with the bromide, and there would be 3 of each of these. We'd end up with the bromide, and we'd end up with the phosphonate at the end. So these are both good ways to exchange. In this case, we exchange an alcohol for a chloride, or if you wanted to exchange an alcohol for a bromide. And we'll get into reasons we would want to do this later in the semester. But for now, just be aware that there are other ways to exchange alcohols convert alcohols into alkyl halides besides adding the mineral acid. The final reaction I want to discuss is the modification of OH. So we would exchange OH for an OH analog. And the reason we would want to do this is to convert OH into what we call a good leaving group, or LG. And again, we'll see why we would want to do this later in the semester, but it's important to note these reactions now so we can use them later in the semester. So we would convert OH to an OH analog, making OH a good leaving group, by the addition of what we call tosyl chloride or mesyl chloride. So tosyl chloride is often abbreviated as TSCl. Mesyl chloride is often abbreviated as MSCl. The structures of those, mesyl chloride is going to be Me or methyl SO2Cl. So this is MSCl. And then tosyl chloride is going to be what we call a toluene group or a toluene group with the SO2Cl. This would be tosyl chloride. So what do these actually do? So what we would do is we would take ROH, and let's just say I'll add tosyl chloride. If you wanted to do mesyl chloride, you would just write mesyl chloride instead. These act the same way. I would add a base, a good base such as pyridine, and the structure of pyridine is as such, where it's got a lone pair, so this is pyridine. That's a good base. And what we would do is we would exchange the ROH plus tosyl chloride. We turn the ROH into ROTS, and we generate an equivalent of HCl. And that's where the base comes in to soak up this HCl. So this OTS, or OMS if you're using mesyl chloride, is going to be converting the OH, which is a bad leaving group, into OTS, which is a good leaving group. So just an example of what this reaction might look like. So say we have the cyclopentanol, and I'll use mesyl chloride in this case, and I add pyridine just to soak up the acid that's generated in this reaction. I would generate OMS and HCl. Again, if I wanted to do this with tosyl chloride, I would generate what we call the tosylate ester plus HCl. And this is going to be converting an alcohol into a good leaving group, which we will see why this is important later in the semester.